The question considers the displacement time graph of a particular gas molecule in a continuous sound wave passing through the gas. So the question wants us to determine the displacement time graph for another molecule that's a distance of 0.289 meters further away from the source as compared to the original molecule. There are a few ways to solve this question, but let's go for the way that allows for the better visualization. So the best way to visualize is actually to consider the displacement distance graph at the instant, which gives us a good representation of all the molecules on the wave at the instant. So let's draw a displacement distance graph for the continuous sound wave. It can be represented just by a continuous sine wave. Right. Let's assume that the source was at the left of this wave, and the wave was traveling to the right. Along this displacement distance graph, let's identify a possible position for the original molecule. Let's call the original molecule A. Right. Based on the displacement time graph of A is supposed to start at displacement equals to 0 when time was 0. And when the time progresses, A is supposed to move up before coming down. So basically, based on how A is displaced from time equals to 0 and how the wave moves, we can consider this particular point to be a possible position for A. Now, let's determine the position of the second molecule on the displacement distance graph. Let's call this second molecule B. To accurately pinpoint the position of B, we first have to determine the wavelength of the displacement distance graph. So basically, we are given the speed is equals to 330. In order to find the wavelength, we need to find V times the period. And for the graph itself, we know that the period is equals to 500 microseconds. Therefore, substituting the values of speed and period into the equation, we'll get the wavelength to be equals to 0.165 meters. We are told that B is at a distance of 0.289 meters away from A, and 0.289 is actually equals to 1.75 lambda. This would mean that B is 1.75 wavelengths to the right of A, and based on the displacement distance graph, we can pinpoint the position of B to be over here. So B at this time, when t equals to 0, is at the positive amplitude position. So based on the options, the only option has to be option 1 for displacement time graph of B. If we consider the motion of B with time, it makes sense that option 1 is the answer, because as the wave travels to the right, we will expect B to move down with time. The displacement time graph of B will be a cosine graph.